change in the distribution of stresses after the stresses at certain points the structure reach yield stress. So at certain point of the structure, if the stress reaches the yield stress, then there is a major change in the distribution of stress. Okay, the theory is that those parts of the structure that have been stressed to the yield stress cannot resist additional stresses. If it is yielded, it cannot resist additional stress. They instead will yield the amount required to permit the extra load or stresses to be transferred to the other parts of the structure where the stresses are below the yield stress. Thus, in the elastic range, unable to resist the increased stress, plasticity can be said to serve the purpose of equalizing stresses in case of overload. So it means that here this we can see this plasticity. That means it can be said to serve the purposes of equalizing the stresses in case of overload. As early as 1914, Dr. Gabor Gazinci, a Hungarian, recognized that ductility of steel permitted a redistribution of stress in an overloaded, statically indeterminate structure. So, ductility only permits the redistribution of stresses in an overloaded or statically indeterminate structure. In the United States, Professor J. Von Brook introduced this plastic theory, which he called limit design. This theory was published in a paper entitled Theory of Limit Design in February 1939. For this discussion, the stress strain diagram is assumed to have the idealized shape shown in figure. The yield stress and the proportional limit are assumed to occur at the same point for this steel. So yield stress and the proportional limit are assumed to occur at the same point for this steel, and the stress strain diagram is assumed to be a perfectly straight line in the plastic range. And beyond the plastic range, there is a range of, here you can see this. This is the plasticity. So this range is assumed to be perfectly straight line in the plastic range. Beyond this plasticity, there is a range strain hardening. This is a strain hardening. This latter range could theoretically permit the steel numbers to withstand additional stresses. But from a practical standpoint, the strains which arise are so large that they cannot be considered. Furthermore, inelastic buckling will limit the ability of section to develop the moment greater than MP. So any inelastic buckling happens, it will not allow the section to develop moment greater than the plastic moment, even if strain hardening is significant. So this is clear, like if inelastic buckling happens, it cannot develop any moment that is greater than the plastic moment, even if the strain hardening is significant. The collapse mechanism. Here we will see about the collapse mechanism. The statically determinate beam will fail if one plastic hinge develops. This is the statically determinate beam. Here two reactions, here one reaction. So this is statically determinate beam. If one hinge forms here, then this is a real hinge, this is also a real hinge. And if one hinge at the center load, if it forms, it will be like a collapse mechanism will happen. Lasting is to illustrate this, that the simple beam of constant cross-section loaded with a constant load at midspan. This is a constant load at the midspan is considered. Should the load be increased until the plastic hinge is developed at the point of maximum moment? This is the point of maximum moment. So at the point of maximum moment, the plastic hinge will develop underneath the load in this case. Okay, an unstable structure will have been created. So this will be unstable structure. Any further increase in load will cause collapse. Pn represents the nominal or theoretical maximum load the beam can support. So Pn is the nominal or theoretical maximum load the beam can support. Let us see one more example. Here you can see for a statically indeterminate structure to fail, it is necessary for more than one plastic hinge to form. So if it is statically indeterminate structure, means more than one plastic hinge is required to plastic hinge required, more than one plastic hinge to form. If it the structure to fail is number of plastic hinges required for failure of statically indeterminate structures will be shown to vary from structure to structure, but may never be less than two. So it will not be less than two in any case of statically indeterminate beam. The fixed beam cannot fail unless three plastic hinges as shown in the part B of the figure are developed. So here one hinge has to develop, here one hinge has to develop, then here one hinge has to develop. So totally three plastic hinges has to develop for this fixed beam to fail. Okay. Although the plastic hinge may have formed in a statically indeterminate structure, the load still can be increased without causing failure if the geometry of the structure permits. Let us see here one more point. Although a plastic hinge may have formed in a statically indeterminate structure, even though one plastic hinge is formed here, still it can the load can still be increased without causing the failure if the geometry of the structure permits. The plastic hinge will act like a real hinge insofar as increased loading is concerned. So this plastic hinge will act like a real hinge, so it will start taking like a wind support. Then once one more hinge develops here, then only it will collapse will happen. So even one plastic hinge formed in static structure, the load still can be increased without causing the failure of the geometry. As the load is increased, there is a redistribution of moment. Once the load is increased, there is a redistribution of moment. Because of the plastic hinge can resist no more moment. So once this plastic hinge forms, it can resist no more moment, so it will redistribute the moment to other parts of the structure. As more plastic hinges are formed in the structure, there will eventually be sufficient number of them to cause a collapse. So once the more number of hinges forms, plastic hinge forms, then it will there is eventually sufficient number of them to cause the collapse. Actually, some additional load can be carried after this time before collapse occurs, as stresses go into the strain hardening range, but the deflections that which occur are too large to be permissible. So here, even though it can we can add some more load before the collapse occurs, but the deflections are would occur are too large to be permissible. Too large to be permissible. It's a too large to be permissible. The property beam of figure 8.9 is an example of structure that will fail after two plastic hinges develops. So after two plastic hinges develops, the structure will collapse. So three hinges are required for collapse, but there is a real hinge on the right end. This is the real hinge on the right end. In this beam, the largest elastic moment caused by the design concentrated load is at the fixed end. So largest moment, elastic moment caused by the design concentrated load is at the fixed end. So largest moment it will happen at here only. Largest moment. Largest moment. So the plastic will happen. As the magnitude of the load is increased, the plastic hinge will form at that point. As the magnitude of load is increased, the plastic hinge will form at this point. So here we can see one more point. For this load, there will be a bending moment like this. So largest moment will be at the fixed end. So if we increase the load, then plastic hinge will form at here. Largest elastic moment caused by the design concentrator is at the fixed end. As the magnitude of the load is increased, the plastic hinge will form at that point. So here if you see, the load may be further increased until the moment at some other point. Here it will be at the concentrator load reaches the plastic moment. Additional load will cause the beam to collapse. The arrangement of plastic hinges, perhaps the real hinges, that permit collapse in a structure is called mechanism. So what is a mechanism? The arrangement of plastic hinges, perhaps the real hinges that permit collapse in the structure is called a mechanism. figures of 8.7, 8.8, 8.9, so mechanisms for various beams. So here we can see 8.7, 8.8. So this is the mechanism for a simply support beam. This is a mechanism for a fixed beam. This is a mechanism for the uh, propped beam. After observing the large number of fixed end and propped end beams used for illustration in this text, student may form the mistaken idea that he or she will frequently encounter such beams in engineering practice. These type of beams are difficult to find in actual system, but they are very convenient to use in illustrated examples. They are particularly convenient for introducing plastic just before continuous beams frames are considered. Here we can see the virtual work method. One very satisfactory method used for plastic analysis of structure is virtual work method. The structure in question is assumed to be loaded to its nominal capacity mn and is then assumed to deflect through a small additional displacement after the ultimate load is reached. The structure in question is assumed to be loaded at its nominal capacity and is then assumed to deflect through the small additional displacement after the ultimate load is reached. The work performed by the external loads during this displacement is equated to the internal work observed by the hinges. Work performed by external loads during this displacement is equated to the internal work observed by the hinges. For this discussion, a small angle theory is used. By this theory, the sine of small angle equals to the tangent of that angle and also equal to the same angle expressed in radians. In pages to follow, the author uses the values interchangeably because the small displacement considered here produce extremely small rotational angles. So as illustration, uniformly loaded fixed end beam is considered the beam and its collapse mechanisms are shown. This is the beam simply sort of means collapse mechanism. So it will two hinges at this here it will form, and also here there is one hinge is formed. So if this is theta, you can say this is theta, and if this is theta, you can say this also theta. So total it's a 2 theta. That's also only a 2 theta. If this is theta and this is L by 2, this is L by 2 theta. Correct. Okay. Owing to the symmetry, the rotations at the plastic hinges are equal. So rotations at the plastic hinges are equal and they are represented by theta in the figure. The rotation of the medial plastic hinge will be 2 theta. So rotation of medial plastic hinge will be, this will be 2 theta. If this is theta and this is also theta, right? And this is L by 2. So this is L by 2 into theta. If you make a straight line like this, you can understand this is theta and this is also theta. One very satisfactory method used for plastic analysis of structures is virtual work method. The structure in question is assumed to be loaded to its nominal capacity. So this structure is loaded to be is assumed to be loaded to its nominal capacity mn and is then assumed to deflect through a small additional displacement after the ultimate load is reached. Once after the ultimate load is reached, it is assumed to deflect through a small displacement after the ultimate load is reached. The work performed by the external loads during this displacement is equated to the internal work observed by the hinges. So work done by external loads equal to work done by internal loads. That's the concept of virtual work method. A small angle theory is used for this discussion. Small angle theory is used. By this theory, the sine of a small angle equals to the tangent of that angle and also equal to the small angle expressed in terms of radians. If this is theta and this is L by 2 and this particular is theta into L by 2. If this is theta, this is 2 theta, and that we can see it from here. Like this, if you draw a parallel line here, this angle is theta, so this angle is theta, this angle is theta, so this angle is also theta, this angle also theta, so this will be the 2 theta. that we have seen it. In pages to the follow, the author uses these values interchangeably because of small displacement considered here produce extremely small rotations or angles. So we will see it here. The work performed by the total external load Wn into L. We have seen that loading is Wn. Wn into L is the total load equal to Wn times L times the average deflection of the mechanism. The average deflection equals to the 1/2 of the deflection. That is nothing but here we have seen right this location L by 2 into theta. L by 2 into theta into 1 by 2 average deflection. So this deflection is theta into L by 2. So average deflection is 1 by 2 times theta into L by 2. The external work done is equal to the internal work observed by the hinges. Internal work means wherever the nominal capacity of moment is there at each plastic hinge times the angle through which it works. So for example, this is the theta. Here one MP is there, right? So MP into theta. Here also MP into theta. But here is MP times 2 theta. So theta 2 theta 2 theta it comes like mn into 4 times theta. This wn into L, that's the load into this average displacement 1 by 2 into theta and L by 2. So total equal wn L squared by 16. So wn, that's the total nominal load, wn L squared by 16. So wn, if you see, 16 nominal moment divided by L squared. So if it is a span is 18 feet span, we can see mn is wn into 18 L squared by 16, right? So 20.25 magnitude. So wn equal to mn divided by 20.25. So here we can see one more example, it seems. So plastic analysis can be handled in a similar manner for the propped beam of figure 8.11 you can see here. Therefore, the collapse mechanism is shown. Here one theta will become, here automatically there is a real hinge, right? A theta will be there, and here also 2 theta is there. The collapse mechanism is shown, and the end rotations equal to each other are assumed to be equal to theta. The work performed by the external load Pn is as it moves through the distance of theta into L by 2. This moves through theta into L by 2, right? Okay. Is equal to the internal work performed by the plastic components at the hinges. Note that there is no moment at the real hinge on the right end of the beam. Here there is no moment. So mn into theta plus 2 theta. So mn into theta plus 2 theta. This is theta into L by 2. This location theta into L by 2. So mn equal to Pn L by 6 or 3.3 times Pn for the 20 feet beam. So Pn equal to 6 mn by L or 0.3 mn for 20 feet beam. So the fixed beam of figure 8.2. Here we can see the fixed end beam 8.2 together with this collapse mechanism assumed angle rotations is considered. Next, from this figure, the values of MP can be determined with visual work. Let us see here. The load here Pn, so it will deflect here. This is the L by 3. So this will be 2 theta. This location is 2 theta and this is theta. So this will be 2 theta times L by 3 and this is 3 theta. Theta plus theta is 3 theta, it will come. Collapse mechanism as assumed angle rotations considered next from this figure value mn equal 2 theta plus 3 theta plus theta. Here also the moment will come, here also moment, here also moment count. So 2 theta plus 3 theta plus 3 theta 6 theta. And Pn into 2 theta by L by 3 equal 3.3 is P equal 9 ml by L equal 0.3 times ml for this beam. Okay. A person beginning the study of plastic analysis need to think of needs to learn to think of all the possible ways in which a particular structure might collapse. Such a habit is of the greatest importance when one begins to analyze more complex structures. So a person beginning to study beginning the study of plastic analysis needs to learn to think all the possible ways in which particular structure might collapse. We need to learn to think all possible ways in which the particular structure might collapse. Such a habit is of the greatest importance. So such habit is very important, greatest importance when one begins to analyze the more complex structures. Whenever we are going to analyze the more complex structure, such kind of habits is one of the greatest importance. Okay. The plastic analysis of proper beam in 8.13 is done by work method. The beam is also beam with its two constants found together with the four possible collapse mechanisms and necessary calculations. It is true that mechanisms of parts B, C, B, D, E of the figure do not control. Here we will see. This is the proper cantilever with the possible mechanisms. Here 2 theta, here real hinge 1 theta, this 10 feet, here 2 theta, so 20 theta. So this 3 theta, this will be 10 times theta. Here it can come 2 theta. And this will become 2 theta, this theta. Here also, this also it can collapse theta, theta. And this also it can collapse like theta, 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 like that, different possible mechanisms. So here MP into 5 theta, 2 plus 3. This is real hinge, real hinge, real hinge. So wherever real hinge is there, we will not talk about that one. Like theta plus 3 theta is the internal load. Here internal load is this and this. Here internal load is 1, 2, 3. So internal load into Mn we have to consider. External load is 0.6 times Pn into 10 theta. This is 0.6 Pn 10 theta, this Pn 10 theta. So what are these vertical displacement that we have to consider? So four different possible combinations are there. Here if you see 0.227, 0.154, 0.13, 0.185. So minimum is 0.154, right? So here we will see that the value for which collapse load Pn is smallest in terms of Mn is the correct value. So, but such a fact is not obvious to average student until he makes a virtual calculation for each case. Actually, the mechanism of party is based on the assumption that plastic moment is reached at both of the controllers simultaneously, a situation that might very well occur. That is a E here you can see in this one. It might very well occur. Location that can reach the plastic locations. The value for the collapse load Pn is the smallest in terms of Mn is the correct value. So for this when the second plastic hinge forms at a Pn concentrated load, Pn equals to 0.154 Mn. So these are the four possible modes of collapse mechanism. So when this load is here, it can, if this can reach the plastic hinge and it can go like this, and it can reach like this, right? And this will be 2 theta, and this is theta because of the real hinge, and this one will become 3 theta, right? So here Mn plastic hinge is there, here also plastic hinge is there. So only these two Mn into 2 theta plus 3 theta, that's the 5 theta, correct? So this 0.6 into here 20 times 10 feet into 2 theta, right? So 20 theta. Here Pn into this distance is 10, this theta, so 10 theta. So Pn into 10 theta, 0.6 into Pn theta. M equal 4.4, Pn equal 0.227. Suppose if this collapse occurs here, it can come like this, right? So it can come other possible combination also. That collapse occurs here. Then this becomes 2 theta, real value. This becomes theta. So this will become 3 theta. Still it will be like here 1 theta, 3 theta is 4 theta, 10 theta, here 20 theta. So Pn into 20 theta, 0.6 into 10 theta, that is here. So Pn value is 0.154. This is the smallest value as compared to all four. So here only starting from here, it can, the collapse mechanism can come like this also. Even it can come like this also. And this is another possible combination. Location of plastic hinge for uniform loadings. There was no difficulty in locating plastic hinge for uniformly loaded fixed end beam, but for other beams with uniform load such as propel or continuous beams, the problem may be rather difficult. Problem may be rather difficult. For this discussion, uniformly loaded prop can beam of 8.4 is considered. The elastic moment diagram for this beam is shown in solid line. This is the elastic moment diagram, and here and the uniform load is increased in magnitude. Plastic hinge will first form at the fixed end. So plastic hinge will first form at the fixed end. So this could be a one question like a plastic hinge where it will first form. It cannot form here because it's already real hinge. It can form at the middle also, but first it will form at the fixed end because the moment is more at this one, right? And this time the beam will deflect. The plastic hinge will first form in fixed end, and this time the beam will in fact be a simple beam. So for as increased loads are concerned, with the plastic hinge on the one end and real hinge on the other end, subsequent increase in the load will cause the moment to change, as represented by the dashed line in part B. So moment will change. It will start to change like this. It will start to change. It will try to increase this, right? Or it will start try to change as shown in the dotted line. Once the plastic hinge forms, the moment will start going like this. So this will be this also mn, this also mn. So both it will reach mn value once the load started increasing it. This process will continue the moment at some other point at a distance x from the right support reaches mn and creates another plastic hinge. The visual work expression for collapse mechanism beam shown in figure 8.41 p mn into theta plus theta L minus x, here this location, right? L minus x 8.14. Yeah, here we can see it clearly. So here plastic hinge formed, here also plastic hinge formed, here L hinge. So theta into some location. This is L minus x by x theta. So this is theta into L minus x, and here it will be theta plus L minus x by x theta. So if you add this one, solving this equation, taking dm by dx equals 0, the x value can be calculated equal to 0.414 L. This value is applicable to uniformly loaded end spans of continuous beams with the simple support ends, as will be illustrated in the next section. The beam and its collapse mechanism are redrawn in the 8.15. And for the following expression of the plastic bond uniform is taken theta 2.414 theta 1.414 0.586 L. So Mn Wn equal to 11.65 MnL by L squared. Continuous beam. Continuous beams are very common in engineering structures. Their continuity causes analysis to be rather complicated in elastic theory, and even though one of the complex exact methods used in analysis, the resulting stress is not nearly so accurate and is usually assumed. Plastic analysis applicable to continuous structure as it is to one span structures. The resulting values definitely give a more realistic picture of the limiting strength of a structure that can be obtained by elastic analysis. Continuous statically indeterminate beams can be handled by virtual work procedures. They were for a single span statically indeterminate beams. As an introduction to continuous beams, example are presented to illustrate the two of the more elementary cases. Here it is assumed that if any or all of the structural collapses, failure has occurred. Thus, in the continuous beams to follow, visual work expressions are written separately for each span. From the resulting expressions, it is possible to determine the limiting or maximum loads that the beams can support. So, one simple example, you will see it here. W18 by 55 section plastic section modulus has been selected for a beam using 50 KSA steel, assuming full lateral, so determine the value of WN. So two span, right? Mn equal to nominal amount is Fy into Z. So we can get this value. Drawing the collapse mechanism for the two spans. This is real hitch. This is this continuous support and this fixed support. So real hinge leave it. So it can collapse like this, and this also it can collapse. So 1.4 on 4. This theta. This is fixed beam kind of thing. 15 feet, 15 feet at center. So left hand span equal to mn into 3.4 on 4. 24 times omega n into half into 14.6. So Wn we can get 9.43. The right hand span equal to mn into theta theta, here 2 theta 4 theta 30. This is 15 theta, here 1 to 4 thetas, right? 30 into omega n, that is the full span, into half into 15 theta. This load is half load, right? So Wn equal to 0.1017, Mn equal to 8.3 kilonewton Gibbs per feet. W21, this also we can see it here. So W2144 consisting of A992 steel Pn. So Pn equal to 15 feet. So theta here and here theta 2 theta, here also theta 2 theta, everywhere like this. And Mn equal to Fy into Z. Mn equal to 3 theta, here real hinge, right? So theta plus 2 theta only. For first and last also real hinge, so only 3 theta. Pn into 15 times theta. Center span 4 theta, it will come 1.5 in Pn into, this is 1.5 Pn. Vertical displacement is 15 theta, so it's 70 kips. Building frames in this section. We'll see here. In this section, the plastic analysis applied to a small building frame. It is not the author's purpose to consider the frames at length this chapter, rather than he wants to show that reader that visual work method is applicable to frames as well as beams. There are other types of mechanisms besides the beam types. For the frame considered, it is assumed that the same W section is used for both the beam and columns. If these members are different size, it would be necessary to take into account the analysis. In supported frame is statically indeterminate to the first degree. The development of one plastic hinge will cause it to become statically indeterminate, while forming of a second hinge can create a mechanism. There are, however, several types of mechanisms that might feasibly occur in this frame. A possible beam mechanism is shown in part B. Side sway mechanism is shown in part C. Combined beam and side sway mechanism is shown in the part D. Critical condition is that one which results in the smallest value of Pn. Plastic analyzer frame, the distance through which the load tends to move in various mechanisms should be carefully studied. The solution for this problem brings out a point of major significance. Superposition does not apply to plastic analysis. This is a very important thing. Superposition does not apply to plastic analysis. This is the one we just wanted to understand. You can easily see this by studying the visual work expression parts B, C, D. The values of P and obtained for the separate of the beam and side sway mechanism do not add up to the value obtained from the combined beam and side sway mechanism. For each mechanism, we want to consider a situation in which they have the fewest possible number of plastic hinges that will cause collapse. If you look at one of the visual work expressions, you will note that Pn becomes smaller as the number of plastic hinges decreases. With this in mind, look at the part D. The frame can be feasibly swayed to the right without formation of the plastic hinge at the top and left column. Two plastic hinges labeled A and B are sufficient for the collapse to occur. And this is the one we have to see it here. This is a frame load 0.6 and PN 20 feet, 20 feet. Okay. B mechanism. This theta and 2 theta, it will come. This is the 20 times theta because it's a 20. Okay. Pn equal to 20, Pn into 20 theta equal to Mn into 4 theta. So Pn equal to 1 by 5 Pn. That's a B mechanism. This lateral sway, if you see, this is theta means this 20, so this 20 theta. So these two hinges happen, right? This is the pinned one, right? So side sway mechanism. So 0.6 Pn, that's the load, and 220 theta. Mn here 1 Mn, here 1 Mn, right? So Mn into 2 theta. So Pn equal to 1 by 6 Mn. But if we combine side sway beam, if you see 20.6 and 20 plus Pn into 20 theta equal to Mn into 4. Here 2 is there. Here and here only mn is there. Mn into data, mn into data, so 4 data. Pn 1 by 8 mn. So this 1 by 5 mn, this is 1 by 6 mn. We cannot combine these two. Superposition is not possible. It's not applicable for this kind of plastic analysis. So here 1 by 5 pn plus 1 by 6 pn we cannot write. This is 1 by 8 pn. It's a combined beam and sideway mechanism, possible mechanisms per frame. So we will see one example. W12 by 72 is used. W12 by 72 is used for a beam and columns on one of the frames for inferior Fy and determine the value of Pn nominal load. Virtual work method expressions are written for 4 parts and so on the respective parts of here. Combined beam and sides is found to be the critical case. 1 by 8 is the critical case. 1 by 8 into Mn Fy into Z. So 52, 56.25. Here you can see 1 by out of 5, 1 by 5, 1 out of 5, here 1 out of 6, here 1 out of 8. So this is the critical, it's the smallest one.